Now that we understand the uncertainty of individual values, let's try to understand the uncertainty of numbers that we actually calculate. So if two or more numbers go into a calculation and we know their uncertainty, what's the uncertainty of the resulting calculation? For this conversation, we're going to stick with some numbers that we saw in the last video. First, we have 200 tons of fuel. That's the amount of fuel that's required for the Mars orbiter to complete its mission. And we also have the weight of the spaceship minus the fuel, which is 3,000 pounds. Now, it turns out that 3,000 pounds is also equal to 1.5 tons. So I've also written down that value so that we can use it in the calculations in this video. Now, before we actually carry out our calculations, it's important to realize that there are two key pieces of information that will allow us to understand the uncertainty of our results. We saw the first type of information in our last video. It's the number of significant figures in the numbers that are going into our calculation. As you recall, significant figures are the known or measured digits in a number. And when you have the number of significant figs in a number, it tells you how many digits are known or measured, but it doesn't necessarily tell you anything about where the decimal place might be located. For example, I could have the number 200 with one significant figure and two zeros that are being used as placeholders, or I could have the number 200ths with one significant figure and 1 0 being used as a placeholder. Both examples have one significant figure, and the number of significant figures tells us nothing about where that decimal is located. Precision is the other key piece of information that we need to understand uncertainty, and it provides information about where the decimal place is located in a particular calculation or measurement. In this class, we'll define precision as the decimal place of the most precise significant figure in a number. For example, if we were to look at the number 200, we have one significant figure, which is this number 2, and it's in the hundreds place. So the precision of this number is the hundreds place. Let's take a look at our 3,000 pounds written in scientific notation. Okay? Because it's written in scientific notation, we can see right away that there are three significant figures. And our most precise significant figure is the 0 listed on the right-hand side. Now you might be tempted to say that our precision here is in the hundredths place because our 0 is located 2 spots to the right of our decimal point. But this actually isn't the full story because our number is being multiplied by 10 to the third. So we need to take this into account before we determine the precision of this number. Now, some of you might be good at doing this in your head, but I find it useful to expand a number in scientific notation out to find its true precision. I know that the number 3,000 can also be written as a 3 followed by 3 zeros in decimal notation. I also know that from the scientific notation that it's the second 0 or the middle 0 here, which is my most precise significant figure. And I can also see that when this value is expanded out, that this digit falls in the tens place. So the precision of our space shuttle weight is actually in the tens place. Now we can also go through this process on our spaceship weight listed in tons. Here we have 1.50 tons. Well, here you might recall that when we have a 0 listed to the right of non-zero digits and to the right of the decimal place, those zeros are significant figures. So in this case, our most precise significant figure is the 0. And this 0 is also located in the hundredths place, the hundredths as opposed to the hundreds place. So the precision of our value written in tons here is the hundredths place. Good. So now we have a good understanding of significant figures and also precision. And as I mentioned before, these are the pieces of information that we need in order to understand the uncertainty of calculations that we carry out. On the lower left, I've listed some rounding rules so we can express the uncertainties of our results. We can start with addition and subtraction. So when we're carrying out a calculation that involves addition or subtraction, our final result will have the same precision as the least precise number that went into the calculation. Let's calculate the weight of a fully fueled spaceship in order to demonstrate this. If we use our known values of 200 tons of fuel and 1.5 tons of spaceship, we should be able to add these values together to figure out what the total weight is of a fully fueled spaceship. 200 plus 1.50 is equal to 201.50. You might be tempted to leave your answer here, but we need to go back to the rule that we just learned and make sure that we're expressing our answer using the correct level of uncertainty. Our final answer has the same precision as the least precise term in our calculation. Earlier, we saw that the number 200 has a precision in the hundreds place, and we saw that 1.50 has a precision in the hundredths place. Our least precise term in this case is 200 with a precision in the hundreds place. Our final answer, therefore, should only be precise to the hundreds place. In order to express our result with the correct level of precision, we're going to round. And so if we round to the hundreds place, we're going to look at the digit to the right of the hundreds place. We're going to look at the tens place. And we see that to the right of the 2 is a 0, and this is going to indicate that we're going to round down. So our final result is 200 tons. Now this may seem kind of strange at first. We started with the number 200, we added something to it, and we still ended up with 200. You might be saying that can't be right, but actually we did everything correct. Now what happened here is that we started with a really large number with a lot of uncertainty associated with it. We started with that 200 value with a level of precision to the hundreds place. And then we tried to add a very small and more precise number to that value. And our result also has a lot of uncertainty associated with it because of the not so precise numbers that went into calculating it. When all is said and done, we can't confidently say that the result is 201.50 as opposed to 210 or 190, for example, just because of the uncertainty associated with that number. And that's what's reflected in our final result when we round it at the end. Okay, next we will explore the rules for carrying out multiplication and division calculations. When multiplying or dividing two numbers, your result will have the same number of significant figures as the factor that has the fewest number of significant figures. In other words, we're going to multiply or divide two numbers. We're going to start by looking at those two numbers and figuring out which one of them has the fewest number of significant figures. Then our result should have that same number of significant figures. To demonstrate this, let's divide the empty ship weight by the total fueled weight in order to find the fraction of total weight represented by the ship itself. In this case, our calculation is 1.50 divided by 200. If we type these numbers into the calculator of our choice, we will see that the result is 0.0075. However, we can't stop here. Once again, we need to make sure that our final result expresses the correct level of uncertainty. So we take a closer look at the numbers that went into this calculation, and we look at how many significant figures are contained in those numbers. In the numerator of our calculation, we have the number 1.50. And earlier we also said that this has 3 significant figures associated with it. In the denominator, we have the number 200, which has 1 significant figure. And our result is going to have the same number of significant figures as the factor with the fewest number of significant figures. In other words, one of our numbers has 3 significant figures. The other number going into our calculation had 1 significant figure. So our result will have 1 significant figure. This means that we will round our result to the first significant figure, which is the 7 in this case. Okay? If we look at the 7 and we look at the value to the right of that 7, we see it's a 5, and that's going to indicate that we round up. So we can write down our final result, which is 0.008. If we want to express this number as a percentage, we multiply by 100, which gives us 0.8%. So the ship itself of the Mars orbiter is less than 1% of the total weight at launch. This is kind of an interesting result. And we know that we expressed our result with the correct level of uncertainty by following the rules that we presented in this video.